Geometry lesson 8.2, the fundamental properties of area. So we dabbled with perimeter in 8.1, and now we're going to look at area. Again, something that you should be pretty familiar with, and we'll obviously take it to another level here in geometry. So the big idea says that formulas for the areas of figures can be deduced from four fundamental properties of area. So what are those four fundamental properties? We see them here in the area postulate: the uniqueness property, congruence property, additive property, and the rectangle formula. It all kind of comes back to that as we study area. All right, so the uniqueness property says every polygonal region has a unique area. We see that here. There's exactly one measure of any given region's area. It can be expressed using different units though. So if I express the area in square feet, it's going to be a different number if I express that same area in square inches, but those numbers will be equivalent expressions. Okay, it's representing the same amount of space, even though we may be using a different number if it represents inches and feet. So that's the uniqueness property. The congruence property says that any two congruent figures have the same area. That should make sense, right? If we know that F and G, those represent two figures, if they're congruent to each other, that means the area inside of them is going to be the same, and that should seem pretty obvious. Letter C, the additive property. It says if you take two regions and you take the union of them, so you're including both of them completely, that's basically just the sum of those two areas put together. And so we take a quick look right here. If we have two regions like F and G that don't overlap, so they're touching, but they don't overlap, the union of those two is the area of F plus the area of G. So if I know the area of this and I know the area of G, and I want to know what's the total area, I can just add those together. That's what the additive property says. Now, I added this quick little question right here just to get you thinking, because that seems really obvious. Is it true that the perimeter of the union of F and G is also the sum of the perimeters of F and G? Why or why not? So if I want the union of the areas of these two, I just add this area plus this area. If I want the union of the perimeters, do I take the complete perimeter of F and add it to the complete perimeter of G? Does that now give me the perimeter of this whole shape? And the answer is no. The measurement of perimeter of this would just go around the complete outside as they're joined, right? And it wouldn't include this part here, which is some of the perimeter of F and also some of the perimeter of G. So the union of their perimeter here is actually going to be much less than if we just added the perimeter of G plus the perimeter of F, because we're not using this middle section for either one. So just to get you thinking a little bit there, but we're mainly going to focus here on area today in this section. And then letter D, basically the area of a rectangle we all know is length times width. The area of everything boils down to that. So when a region is the union of rectangular regions, you can just apply the area postulate to find its area. Area equals length times width. So we have length times width here, 5 by 4. If you want to know the area, you just multiply 5 times 4, and it's 20. And early on in elementary school, you looked at stuff as simple as this. 5 units across, 1, 2, 3, 4, 5, 4 units down, right? Each one of these squares represents a 1 by 1 unit, whatever it is, a square inch, a square foot. And if you added all these up, there's 20. That's the same as multiplying length times width. So everything kind of boils down to that. All right, so let's jump into some questions. So I'm pretty confident that many of you could reason through this, and there's no special tricks here that we're going to add. I think you already have all the skills that you would need to solve this problem. But this is a multi-step problem, so we want to make sure we're all staying together. And it's kind of spelled out here in steps for you. Now, you could definitely accomplish this going in a different order than these steps. The final question says, what will the paint cost for this job? You could probably get there without going exactly through these steps, but we're going to walk through it very linearly here, step by step, and get to a final answer. So painters have been hired to paint one wall of an auditorium, which is pictured here on the right. They need to calculate how many gallons of paint they need to purchase for the job. So the specifications are as follows. The wall is 60 feet long, 18 feet high, as you can see. So before we move any further, we want to figure out what's the area of that whole shape. Now there's windows, and we're going to have to take those windows out of the area. But first we need the entire area before we can do anything else. So the area of this rectangle, length times width, is going to be 18 times 60, and that is 1080. Okay, so there's our step one. There's 5 windows along the wall, and they measure 3 by 7 each. Okay, so these are 7 by 3. So we're obviously not going to paint the windows. So we want to know the area of them. Well, we know, right, we can just write this in here. 7 times 3 is 21. So the area of each one of these windows is 21, each one individually, and there's 5 of them. So 21 times 5 equals 105. So the combined area of all the windows is 105 square feet. So if they did not exist and you were going to paint this wall, there's 1,080 square feet. We're going to take off, so 1080. We're going to take off the space that the windows take up because we don't have to paint that. So that's going to leave us 975 square feet that we need to paint. Okay, next, a gallon of paint will cover approximately 350 square feet. Okay, so if I've got 975 square feet, we might as well label that square feet. Looks like that. How many gallons is it going to take? So I'm going to divide 975 divided by 350. So 975 divided by 350. 2.7857. I'll stop there. Next step. So that means it's going to take more than 2 gallons. So far we're needing 3 gallons of paint. But then they give you more information. The wall is going to need 2 coats of paint. So this is how many gallons it would take just to paint it once. We got to paint it twice, 2 coats. So let's take this number and times it by 2. So times 2 now is going to equal 5.5714 gallons of paint. So that's how much we have to buy. Now you can't go to the store and buy 0.5714 gallons. You've got to buy. Now there are smaller portions that you can buy, right? You can buy half a gallon and all different sizes. But for the sake of this question, we're going to say that you have to buy a full gallon. Each gallon costs $14.95. So we're going to have to buy 6 gallons total. And so we're going to times that by $14.95. So 6 times $14.95 is $89.70. So the cost of the job will be $89.70. They will have a little bit of paint left over, but if you just bought 5 gallons, you would not have enough to cover it with 2 coats. All right, and then down to the bottom. So changing units of area. Anytime we're converting units, this can be a confusing part for students. Going between feet and yards, inches and feet and miles, whatever it is, those conversions can cause a lot of headaches. So let's take a look. So from the rectangle formula, all our other area formulas can be deduced. So they all come back to that. For instance, a very simple comparison here. How does the rectangle formula relate to the formula for a square? Well, a square, as we've studied with the hierarchy, is a rectangle. It falls under it. So it should follow the same properties, and it does. If you know the sides of a square, you can do length times width, and you're going to get the area of it. Now, what's special about a square is all the sides are the same. So if the side's 5, so is this one. So length times width is going to be any number times itself, 5 times 5 or 10 times 10. In this case, s times s. So instead of writing it length times width, we know it's just going to be some number times itself, which is that number squared. And so when we see the area of a square expressed specifically, it's going to say area equals the side squared. We only need one number, one side, and we just square it because we're timesing length times width. Now, let's get into these units. Many abbreviations are used for the units of area. For example, 1 square yard can be written as 1, and then square yard is abbreviated like this. But more often than not, you're going to see it yards squared. Now, a lot of students will read this as 1 yard squared, but we read this as 1 square yard or square feet. And that should seem pretty common when you first look at it. You, of course, want to just read it the way you see it. But if you talk about how many square feet are in your house, you're used to saying those words. You don't say how many feet squared are in your house, right? That just doesn't even sound right. That sounds more mathematical than it does everyday life. So it's 1 square yard or 1 square foot. All right, so it's asking us now, how many square feet are in a square yard? So when we're talking about a square yard, we're talking about 1 yard by 1 yard. How many square feet are on the inside of 1 square yard? So length times width, if we're just keeping it in yards, is 1 times 1. Okay, so that's how we get 1 square yard. We know that 1 yard is 3 feet. So if you take a look at this picture, I'm taking this, transporting it over here. This top is 1 yard, but now if I split it into feet, it has 3 feet. And then the height here, which is also 1 yard, is 3 feet. So 1 yard times 1 yard is the same as 3 feet times 3 feet. 3 across, 3 down. So 3 feet times 3 feet is the same as 1 square yard, as you can see in this picture. And so 9 square feet, because 3 times 3 is 9, and you can count, you've got 9 of them here, 9 square feet. 9 square feet is the same as 1 square yard. So this represents the same unique area. Okay, we're expressing it with different numbers, but it's the same area. This is 1 square yard. This is 9 square feet. Okay, I haven't changed the area. I'm just expressing it differently. All right, so let's look at example number 2. How does this come into play? Well, it kind of gives us some options on how we can compute some of these problems. You can do them in different orders. Basically, you can convert at the beginning or you can convert at the end. So suppose a farm is, so I'm going to kind of draw this, it's a rectangle, 1/2 mile long and 1.5 miles wide. So I didn't draw this to scale, but if it's 1.5 miles wide and half, so 0.5 a mile long, it looks like this. So the question is not how many square miles is it, that would be easy, you just multiply those two numbers and you're done. How many square feet of land is this? So we can very easily find out the square miles, but how many square feet is this? So there's two different ways to do this that we're going to look at. So for solution 1, we're going to convert the dimension to feet first. So we're going to take this picture, and instead of writing it in miles, we're going to write it in feet. So 1 mile is 5,280 feet. So 1.5 miles, we're going to take 5280 and we're going to times it by 1.5. So that's equal to 7,920 feet. So I've simply just converted this. I'm not talking about the area yet. I'm just talking about the length. And then I'll do the same thing with 0.5. 0.5 miles will be half of this number. So 5280 times 0.5, or of course you could divide by 2. It's 2640 feet. And so now I can very easily find the square feet of this land because area is length times width. So area equals, and it really doesn't matter which one you call length and width, so 7,920 feet times 2,640 feet. That will give us the area here. Okay, and you get this really big number, but that should make sense. We're talking about miles of land here. So there's going to be millions of feet, right? That should make sense. So that number here is 20,908,800. And I multiplied feet times feet, so that's square feet. So that is actually my final answer. And I think that's the easier way to do this, but we will look at a different strategy that may make more sense to you, but I do think this is the easier way to do it. Convert it first, and then just go ahead and find the area like you normally would. Now let's say you're going to find the area in square miles first, because you could figure out, okay, this is how many square miles. So area equals length times width. We're just going to do it in square miles, and then we'll convert it to square feet. So I'm doing 1.5. I'm going to use parentheses for multiplication just so that the decimals and the multiplication symbols don't blend together. Okay, so multiplying here, 1.5 times 0.5. That's going to be 0.75 square miles. Now that doesn't answer the question. Okay, the question says how many square feet. So this is 0.75 square miles. How do we convert that into square feet? And we already know what the answer is here. So you could play around with your calculator and try a bunch of different things. Okay, but let's break this down to just 1 square mile. Remember what 1 square mile is? It's literally a square that's 1 by 1. So when I multiply that, 1 times 1 is just 1 mile squared. So what does that look like in feet? Well, this mile up here is 5280, and this mile down here is 5280. And so 1 mile squared is equal to this times itself, 5280 times 5280. That would be the length times width. We did 1 mile times 1 mile. If we're going to do it in feet, though, it's 5280 times 5280. So I'm going to write this as 5280 feet squared. 1 mile times 1 mile is the same as 5280 feet times 5280 feet. 1 mile squared, or 1 square mile, is equal to 5280 squared. So let's go ahead and actually figure out what that is. So 5280, you could use the squared button, or you could do 5280 times 5280, right? Just like the length times the width, anything times itself. So 1 square mile is 27,878,400 square feet. Now, notice that answer doesn't match. This is how much 1 square mile is. We've already calculated this is 0.7 square miles. So this is less than 1 square mile, smaller than this one that we just calculated. But this is how much 1 is. So if this is 0.75 of that, we're just going to multiply this times 0.75, and boom. There's our magic number that we already calculated over here, 20,908,800. So I think that's way more confusing, but let's talk through it and make sure we understand it. If you were going to do this problem, I would suggest you do it this way. But to understand both of them, if you could explain both like I just did, you're thinking at a higher level than just, okay, memorize that I do it this one way every single time. But what happens when I get stuck? Can I think outside the box? So again, what did we do over here? Just to go over it one more time. First, we found the area in square miles. We didn't convert anything to feet. So we did 1.5 miles times 0.5 miles. So that's 0.75 square miles. We need to convert that into square feet. So first we need to figure out 1 square mile is how many square feet. So we did 5280 squared. We got this really big number. That's how much 1 square mile is in terms of feet. So now that we know we're dealing with 0.75, let's say we're even dealing with 10 square miles. Well, then you would just multiply this by 10, whatever it is. So 1 square mile is this many square feet. So we just take what we're dealing with, 0.75 square miles, and multiply that times this, and boom, we've got our square feet.